All right, let's dive right into this explainer by asking a pretty simple question. What actually happens when the relentless march of our digital world crashes headfirst into the physical limits of the universe? Today, we're exploring a technological marvel that single-handedly dictates the future of our modern world. It is, frankly, a story of impossible engineering, and we're going to break it all down.
To understand exactly how we avoided the death of Moore's Law, we'll walk through a structured journey. We'll cover 1. The most important machine. 2. Hitting the physical wall. 3. How EUV actually works. 4. Vaporizing tin with lasers. 5. Decades of extreme engineering. And finally, 6. The high-NA future.
Section 1. The most important machine. We are kicking things off with the absolute most vital piece of hardware in the modern world.
The sheer cinematic scale of an ASML extreme ultraviolet or EUV lithography machine is just staggering. Costing hundreds of millions of dollars each, they are these sprawling labyrinths of extreme engineering that use invisible light to print microscopic microchip features. We're literally talking about the foundations of the entire global digital economy being forged inside these massive boxes. The complexity inside these units is so vast that it requires multiple 747 aircraft just to ship a single machine to a chip-making facility. Part 2. Hitting the physical wall. Let's see how this entire technological leap builds from a very specific, microscopic problem. Tracing the history here, the semiconductor industry successfully shrank lithography resolution over the decades, which is exactly how they kept Moore's Law alive, making our tech faster, cheaper, and vastly more powerful. Back in 1984, we were working with resolutions larger than a micrometer. Step by step through the 90s and 2000s, engineers used deep ultraviolet light to push all the way down to the 32 to 20 nanometer range. But eventually, they hit a physical wall. The paintbrush of standard deep ultraviolet light was simply getting too wide for the atomic scale canvas they were desperately trying to paint on.
So engineers had to make a dramatic leap to a wavelength of exactly 13.5 nanometers. To put that into perspective, this is right on the edge of the X-ray range of the electromagnetic spectrum. It was absolutely essential to keep packing billions of transistors onto a single microchip, but manipulating light at this wavelength is, well, incredibly difficult. It fundamentally behaves differently than visible light. Because it's so close to X-rays, it doesn't just pass through glass or bounce off regular mirrors cleanly. It gets completely absorbed by almost every single material on Earth.
Section 3. How EUV actually works. Generating and using that 13.5 nanometer light is essentially an act of forcing the universe to do something it really doesn't want to do. To print these incredibly intricate foundation layers, a silicon wafer undergoes a highly precise sequence. First, the wafer is spin-coated with a photoresist. Think of it essentially as a light-sensitive chemical layer acting a lot like photographic film. Then comes a post-application bake to set that layer. Step 3 is the critical moment, the actual EUV exposure, where the blueprint of the chip is optically projected onto the wafer itself. Finally, a post-exposure bake and development wash away the unexposed resist, revealing the intricate microscopic pattern left behind. And to achieve this, you need multi-story cleanroom components maneuvered by massive cranes just to manipulate elements at a fraction of a human hair. The juxtaposition of building-sized machines required to do atom-sized work is simply astounding. It literally takes macro-level industrial engineering to achieve nano-level precision. Looking inside the optical column of this twin-scan system, we run into a massive engineering hurdle. Traditional glass lenses completely absorb 13.5 nanometer EUV light. If they used normal lenses, the light would just vanish. So the system instead uses a highly complex series of ultra-smooth, multi-layer mirrors. These mirrors are some of the flattest surfaces ever created by human beings. They carefully guide the light and shrink the reticle pattern by a factor of 4 before it ever even hits the wafer. Section 4. Vaporizing tin with lasers. Now, knowing how we bounce the light around leaves an obvious question. Where does this incredibly elusive 13.5 nanometer light come from in the first place? To find out, we have to zoom in on the plasma vessel. This is the violently energetic heart of the machine. At its core, an immensely powerful CO2 laser acts as the driver to generate the EUV light. What happens next inside this chamber is nothing short of science fiction happening in real time. The engineering numbers here are almost comical when you say them out loud. The system literally drops microscopic liquid tin droplets into the vessel. These droplets are traveling at 150 miles per hour. While in midair, they are struck by twin laser pulses 50,000 times every single second. The first pulse flattens the tin into a pancake, and the second vaporizes it into a plasma that sparks a brilliant flash of extreme ultraviolet light. All of this coordinated, high-speed chaos, just to generate the light needed to print the chip. And here is the real kicker. Because that newly born EUV light is absorbed by literally everything it touches, you can't just shine it right through a normal room. The entire optical path, from the light source, bouncing off all those beautifully flat mirrors, all the way down to the silicon wafer, must be contained in a strict high vacuum. Even a single, tiny pocket of regular atmospheric air would absorb the light before it could ever do its job. Just maintaining this vacuum across such a massive machine is a monumental feat of its own. Section 5. Decades of extreme engineering. Pulling this off wasn't some sudden eureka moment. It required an exhaustive, collaborative marathon. When you map out the history, you realize just how long the runway actually was. The initial concept began floating around back in the 1980s. ASML didn't even formally begin their R&D until 1999. By 2012, they acquired Cymer to completely control that crucial light source technology. It took over 2 decades and a staggering 6 billion euros in research and development to finally push EUV from a theoretical chalkboard concept to high-volume commercial production around 2018.
And ASML absolutely didn't do it entirely alone. The breakthrough required unprecedented collaboration. Early industry-funded engineering test stands were developed alongside U.S. national labs, places like Berkeley, Livermore, and Sandia. This was a massive, multinational, multi-institutional effort just to prove the physics could actually work in the real world.
They also had to overcome massive skepticism. For years, critics loudly claimed EUV would never be commercially viable. It was too expensive, the light source was too weak, and the machines were just way too complex. But looking at the leap,
From shipping a clunky experimental demo tool for research back in 2006, ASML managed to ship their 100th commercial EUV system by 2020. That milestone completely redefined global semiconductor manufacturing. It proved the skeptics wrong and kept the whole digital revolution securely on track.
Part 6, the high NA future. But hey, the physics-defying innovations didn't stop in 2020, which leads us to our final chapter. To keep Moore's Law alive into the next decade, ASML engineered the EXE platform. They didn't just tweak the old machines, they physically redesigned the optics entirely and introduced significantly faster wafer and reticle stages to improve the overall speed and precision of the printing process.
The vital breakthrough here is all about numerical aperture, or NA. Think of NA like the size of a camera's lens opening. A wider opening captures more light and finer details. They managed to increase the NA from 0.33 in previous generations all the way up to 0.55 in the new EXE systems. This jump provides dramatically higher contrast, allowing chipmakers to print microchip features with an astonishing resolution of just 8 nanometers.
What this means for the industry is just profound. By reducing the number of complex process steps in manufacturing, these new EXE systems make it commercially viable to physically shrink chip architecture into the sub-2 nanometer range. The high-volume manufacturing of these incredibly dense, lightning-fast, and power-efficient chips is slated for 2025 and 2026. This practically guarantees our phones, computers, and AI servers are going to keep getting exponentially more capable.
So as we look back at these monumental machines that drop liquid tin at race car speeds, vaporize it with lasers in a total vacuum, and bounce invisible light off perfectly flat mirrors just to print the microscopic foundations of our digital future, we have to ask ourselves something. When we finally hit the absolute limit of what 13.5 nanometer light can do, what completely impossible boundaries of physics are we going to have to shatter next?